So my presentation is on guitar, sound, and sine waves. So my question was, how does a guitar make sounds, and what's the sine equation that shows this, and how it's demonstrated through its sound waves? So what I did was, Steve and I used Logger Pro and the data logger to record as I strummed an A chord. So I did this chord.
Just a string, right?
Just a string, yeah. And so then we graphed it and found the FFT of the graph, which is just the basic movement of the sound on the string. And we zoomed in on the vibrations and noticed the patterns, which is based off the fundamental frequency. And so this is the A string, and they each vary in a different thickness, which gives it a different sound. So the definition of frequency is the rate of cycles of vibrations per second measured in hertz, or it can be any time unit, but seconds is the most reliable because they move so fast. And so the frequency of a properly tuned A string is 110 hertz per second. So each individual vibration is based off of the one frequency of 110. So it always has that same frequency, but depending on the amplitude, it changes to multiples of 110. So 220 hertz and 330 hertz, and even 440, etc. But they get so small that the main ones are just 110, 220, and 330 of the different amplitudes. And so those different vibrations are seen in the green line, which is the green line is the sound that is directly put into the data logger. So everything that the logger hears is in the green one. And then the vibrations, these three all add up to make one big sound that we hear because they move so quickly. And that is in the black line that is put up against it. So each of these is one of the vibrations. So the 110 vibration is this graph. And since they're the latter ones, they're moving at sort of a slower pace. And then we see the 220 and the 330, and these are so close together as they get to be the farther along vibration. So the math behind it. So frequency, since it's the number of cycles in 1 full second, you can solve it based on to figuring out the amplitude and the different things about the wave. And so I used the sine equation because that was the most relevant to these sound waves. And so amplitude is the volume of the sound and also the distance from the highest point to the center line, which I figured out is 0.00045. But since it's dependent on the different types of vibrations, they all have a specific sound wave for each amplitude. And this is just my math for the period. Since it's 1 second divided by 110 hertz, or 1 cycle, you get 0.0099. And then you do that, 2 pi divided by that to get your B. And so for your equations, then the B will be the 690.869 for the sound. And so once I have these, you can sort of determine the different movement of the wave. And so the final equations from Logger Pro are the main fundamental one, which is going to be used for most A chords because it's for the 110, which is the direct frequency, is 0.013 times sine 690 times x plus 0.0033 plus 0.0044. And then these are the different equations for the different amplitudes of vibrations. So you can get different ones for each of the A chords, but this is the most relevant because it's based off of the single frequency. And so my explanation, the final conclusion of how the guitar makes sound, is that each string has a different thickness, which makes that pitch. And so when you strum, it causes different vibrations in the air because the reason that sounds are in waves is that the sound waves are created from the vibrations of air, of sound particles through the medium of air. And so the equation is based on the specific string, but in general, each string makes the different noises based on so many different vibrations within that string of that frequency, and they all combine to make the noises that we hear. Questions? Good.
So, I'm no guitar expert, I don't play, but the top 3 strings are a different material than the bottom 3, correct?
I think so. Yeah.
Does that cause like a drastic like if you were to play the 3rd string versus the 4th, even though they're very similar in size, would that make a drastically different graph because of the different like weight to each?
I don't think they'd be completely different because they're similar enough in size, but the different material and sizes definitely make them sound slightly different. So this would be one of the top, and then this would be one of from the bottom. So it's definitely higher, but I guess not so much more as the other ones are from each other. Elsie?
So this is how a guitar tuner works, right?
Yeah.
So
The tuner will give you the pitch, and you try to get it to that exact frequency. So your tuner will automatically give you, depending on the type of tuner, mine sets off a green light once you've reached the right frequency. That's all.
And how do you reach that right frequency when you're tuning?
So when you're tuning, you move it to make it tighter or looser, depending on, and so the tighter you make the string or looser once you fit it to that exact frequency, that's how you get it. Tom?
You probably said this, but I missed it. So were you saying that like the A was it 110?
No, the A, well, it is 110 because that's the frequency, but it changes depending on the different amplitude of yours. So, can we go back to that one, Maddie? It's just a side
which
It's the second to last,
second?
the 11th, or 10. Thank you. So for this one, the different amplitudes are all kind of based off of the distance from the highest point or lowest point to the center line. And so they have different distances depending on the waves. But the amplitude of how loud it is going to be depending on these different parts of the frequency, which is the multiples. But the actual A value amplitude will be the distance from the highest or lowest point to the center line. And then how loud it is will be based on that frequency.
Wait, guys, between. So I assume that the 110, or 220, 330, that was like a higher A and a higher A. Is that not?
Yes, those are the amplitudes in the volume, but the actual A value in the equation is going to be different.
Thank you.
Can you share how the original, when we recorded the sound,
Yeah.
could we go to that,
Oh, yeah.
that
It's
graph?
if we go up to the green one. Thanks, Maddie.
Where are we going?
Right here.
6.
6. Cool.
Yeah.
Yeah.
So you,
So this is how it works.
can you explain, I don't know whether everybody's capturing exactly what you did there.
So when we press up the data logger to the guitar, it recorded this green line, which is the different sounds. And so as it gets further along, these show how loud it is. And then the actual, so the amplitude of how, basically the highest points of how loud it was would be the 110, 220, 330. And then the actual value of amplitude will be the distance from the highest or lowest point to the center line, which is normally 0.0045. And so the actual black line, since these vibrations each add up to make what the green line is, that's what the black line is. It's just the add up of these vibrations. And it's a lot smoother than the green line because it's not based off of a recording, so there's no outside influences.
I still need, with that slide, that was the one that I didn't get. Is that you plucking one string?
Yes.
Okay, and that's over time. Wow, it's amazing there's that much difference.
Yeah, and that's only in 0.04 seconds. It's like there's so many per second.
How many per second?
110.
10. and how did you figure out that black line?
So how you figure out the black line is on LoggerPro, there's a button that's analyze and model, and you can change your different equations to make different ones. And so we tested out, Steve and I, a bunch of different equations to figure out what was the closest to this. depending on, we kept the equation relatively the same as this one, which is the 0.013, 0033, 0.0044, which is the same as our final equation, because, and then we would test little values for that to alter it so that it became roughly the same as this.
It's amazing that you think that those three waves that look really clean and perfect,
Yeah.
when you add those three waves together, you get this,
Yeah.
right? Which is that one string being plucked,
Yeah.
you know?
Is it really true that it's different octaves in A, or is it other sounds? That just an A string makes, a guitar A string is made up of like all these different sounds?
I think it's all based off of, I'm not sure the exact part of it, but I think it's kind of all the different sounds come from the different octaves. So they're all octaves of the same 110 frequency, and so which varies different sounds. But they're all the same based off of that frequency.
Okay.
Yeah.
I wonder if you're getting resonance from the other strings. Is that possible? I mean, that's a whole.
These are harmonics of one another. So what's happening is the string is, if you imagine a large rope, and we were playing Dutch, right? So it's got one loop, right, like this. Well, if I came in the center and grabbed it right in the center, and I did it, I'd have two loops, right? Well, that would mean twice the frequency. And then if two people came in and grabbed it, there would be three loops.
Yeah.
Does it make sense? So you're always going to have multiples, integer multiples of the original frequency, right? And that's what these things are.
And they
And
make different
you can see the
shapes.
propensity of one over the other, right? You did a really nice job, Jenny. You can see that the first one is the principal fundamental. It's the largest contributor. Right, and then the second one is a little bit, right, Jenny, when we were fixing it, we recognized the amplitude of that one needed to be smaller, right?
So much more.
Yeah, and the third one's larger. So it's really kind of a simple act, turns out to be a little bit more complex. Nice.
Thank you.
Thank you.